All right, so now you guys understand that the intensity, frequency, duration data is a data that says over 5 minutes, you're going to have this amount of rainfall. Over 10 minutes, you're going to have this amount of rainfall. This data can be found at the Bureau of Meteorology. Here you have rainfall IFD data systems. Design rainfall, search for single point, map preview, right? So you go here to the map. Really? I don't know. Can I just have the map? Select from map. All right. So I'm not impressed with this website, to be honest. So you go somewhere on the map, and then you want to download the IFD data. You go here, and then you submit it, and you're gonna get this data, this table chart. You need millimeters total or millimeters an hour, and you see this. But you don't have to do that because our website literally hits BOM on the API and gets all the data automatically. Going back to our website, there's some information how you distinguish, and then there's a little bit of paper here discussing the difference between IFD data and continuous data. On BOM the Builder, you can see, as I said, yearly rainfall, annual rainfall, or rainfall in February. For example, it's going to take a bit to load up. Then you have the scale here. You can see it in September, so on and so forth. You can show the rainfall stations that have generated all this data. And see, this is how I know that the IFD data is half of it black magic, because we don't really have rainfalls in here, right? The IFD data comes at in squares that are roughly 2.5 by 2.5 kilometers. There's no way you could have a data to really know exactly why the IFD is here versus here, right? Or more towards where you guys are, here, right? In Brisbane. There's just no way. There's just no way to know with exactity that this rainfall here is different than here. Anyhow, the IFD literally says, all right, there is a one flat value at 5 minutes, 108, 123 flat value millimeters an hour. At 25 minutes, 65. And this is intensity, frequency, duration data. This is used for flooding, for stormwater quantity. Now, well, let's see what kind of data was used to statistically generate the IFD. The kind of data that was used to statistically generate the IFD is this kind of data. The blue are the rainfalls at every 6 minutes. Every 6 minutes you have a bit of rainfall. Sometimes you have none, sometimes you have some. The green is the IFD data overimposed over this 6 minutes information. So 4 EY means once every 3 months. I had to do the calc. 4 EY is once every 3 months. 3 EY is once every 4 months. 2 EY is once every 6 months. You get it. 63.2 AEP is roughly once every year. This one roughly once every 2 years, right? So we have here 10 years of data. How did I get to this information, by the way? What did I do? I went to John Connor Online, so on Stormgate. I went here, I just pressed John Connor Online, and John Connor Online has uploaded, and I pressed on this rainfall button right here. This rainfall button right here shows me the continuous data that we use in that location. So now we're getting a little bit deeper into stormwater quality. Stormwater quality, as we discussed before, worries about maximum flow. Now, stormwater quality doesn't concern about the flow, how it comes over 1 minute or over 1 hour. In this particular instance, you just hold the water back into a tank and then you just release it at the maximum peak flow for that situation. Over doesn't matter how long, it's irrelevant. What's relevant is that you don't go over the peak.
Now, this doesn't really consider dynamics in the creek, hydrodynamics in the creek, how the water flows, the flood wave when it comes from where, how. This is different. But let's instead of thinking of creek, think of pipes. You have a council pipe. You discharge into the council pipe. The council pipe has a certain capacity, and you do not want to go over capacity because then it's going to bubble up and flood somebody, either where you are or downstream or both. Yeah, let's think about pipes. As you can see, whether it reaches the peak once or goes over the peak continuously, it doesn't matter. This is a simplification. In stormwater quality, we don't necessarily care too much about peak. We care about volume over time, because the water will carry some volume of pollutant. If it rains really hard one time and it flushes a lot of pollutant down the river, maybe that's okay. Why is that okay? Because a lot of the pollutants happen at lower flows. So let's go back. You go to the rainfall in John Connor online, and this is the graph that shows you the rainfall over time. In this particular instance, it's 10 years, 1980, 1990. This is called water continuous modeling. The original software that did this starting back in the 90s was MUSIC, Model for Urban Stormwater Improvement Conceptualization. You will see here people saying MUSIC model here, MUSIC model there. There's nothing special about MUSIC. It's simply a continuous model. So at every 6 minutes, you have information. Has it rained? Hasn't it rained? Has it rained? Hasn't it rained? You can see the spaces between these blue lines. That is because there's a lot of time when it doesn't rain. Actually, if we look at advanced statistics, which is something I'm proud to have invented, this advanced statistic, total days, 3,353, total 6-minute intervals, 876,000, and total and days with rainfall, 1,289, days without rainfall, 2,364. Total non-zero rainfalls means maybe I should rename it. You see, we have total 6-minute intervals, 876,000. Total intervals when it's non-zero, therefore it rained a little bit, 80,000. So about roughly 10% of the time it rains, not more. Roughly 10% of the time. So at any 6-minute interval, if you step outside and you know nothing about anything, you have a 10% chance that it rains. Well, a little bit less than 10 in this instance. All right, so look at that. We all even have total number of events, cluster rainfall intervals. But what you will find with this information here is that this is at 6 minutes. There's no half an hour interval when the rainfall is flat. This is how you know the IFD data is a little bit made up. This is at 6 minutes. The IFD is at 6 minutes. If the IFD was at 12 minutes, you would have to have a 12 minute, two of them at the same level. If it was at 2 hours, 2 hours at the same level. But this is kind of a way to overlap the IFD over the data that you have and kind of figure out, does it make sense? So we have 10% AEP here. So in once in 10 years. And look at that, it actually makes sense. Once in this 10 years interval, we have a rainfall that goes there. 20 is twice. We have 1, 2, 3. I think we have 2 of them here. So we have 3 in 10 years. Three instead of 2. Again, this is a little simplified. AEP is the average exceedance probability. We can go into the statistics, but for the purpose of this exercise, kind of like that's what we're thinking. 50%, you should have 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, we have a little bit more. All right, so that's the continuous data. This continuous data will
create volumes of flow, not peak flow or not volume for one event, just volumes over 10 years. These volumes of flow will carry with them pollutants. There's something called pollution generation curves or values, and each surface will generate some pollutants. This data, you will feed it into what? Into your modeling value, or sorry, into your modeling software, Music or Joncon Online. Now you guys can see that there are different colors on our map. Now, and then you can see that the colors don't really match the lines. They don't really match the lines because we have to make a compromise between speed and super duper accuracy when you look at it. Like in the back end, the lines are going around, but for the purpose of just looking at it, we just loaded up less points. So actually the map is faster to load. Now, Australian internet is not always the fastest. So everywhere there's a different color, there is a different rainfall that is used in that location by council. Typically, the data that you need to create a model to tell you how much pollution you generate is specified by council or by some other authority. Now, as the council specifies the data, okay, so you can see here, this is Gold Coast North, Central, and South. They have three locations. Every different color loads up a different meteorological template. Every different meteorological template, which is this bit here, has a different rainfall, and this is the evapotranspiration. So how much water evaporates and transpires. As the basis of the data set for modeling. Now, in order, like as an educational thing, you might hear people saying first flush. Well, we have some information if the first flush is relevant or not. And I think we have some lecture here about stormwater quality, and I highly recommend that you watch it. This is a lecture that I held at University of Newcastle. Now, we also have some case studies, how to model things, and it's probably important to, maybe we have a little bit of time, maybe not, to talk about source nodes and treatment nodes. I think maybe I will let Greg talk to you guys about source nodes and treatment nodes. But yeah, important, really important to look at how the graph, how the rainfall looks, and to understand the difference between IFD data and continuous modeling. Many times you will hear councils or people saying, oh yeah, the GPT has to handle 1 in 3 months. And I'm like, I'm sorry, what? No. Why the GPT doesn't need to handle the 1 in 3 months? Why the sediment basin doesn't need to be designed for 1 in 3 months? Because the 1 in 3 months is a make-believe number. And the reason why you have a model, the simple reason why you build a model for stormwater quality is so you can figure out what the high flow bypass for that device is. High flow bypass is simply, you can chuck into a gross pollutant traps, which stops all the sediment, stops some sediment and all the gross pollutants like leaves, sticks, and stuff. That can have the capacity to treat, let's say, 20 liters a second, or 30 liters a second, or 40 liters a second. Of course, if it treats 40 liters a second, it's a bigger device, costs more. 20 liters a second is a smaller device, typically costs less. So then, how do you size how much flow can it handle? Because as you see from this graph here, there's a lot of the volume is under, some value. As you actually, it's from this graph here, you can see exactly total volume under, right? One in 3 months, you treat 97% of the value. Anyways, you size it with the model. You don't size it just because rule of thumb 1 in 3 months. What is this? What's happening?